Welcome to Lesson 5.5 Advanced Chat Techniques. Overview. This lesson is where your chat model stops being a text predictor and starts becoming a capable agent. You're going to learn 4 techniques that separate toy demos from production-grade AI systems: function calling, structured output generation, RAG integration, and agent-style behavior. Each one unlocks a fundamentally new category of what your model can do. Plan for about 90 minutes. This is advanced territory, and it's worth taking your time with. Learning objectives was QoS. Jukans ones that you can study EKS quickly. By the end of this lesson, you'll know how to implement function calling so your model can invoke external tools, generate structured outputs reliably so downstream systems can parse the results, integrate RAG so your model can reason over private or recent data, and build agent-style behavior where the model plans, acts, observes, and adapts. These aren't isolated tricks. They compose together into genuinely powerful systems. Technique 1. Function calling. Tool use. Here's the core idea behind function calling. The model doesn't execute code. It decides when a tool is needed and generates a structured description of what to call and with what arguments. Your application code does the actual execution, then feeds the result back into the conversation. The model is the decision maker. Your runtime is the executor. Walk through this flow carefully because the pattern repeats everywhere. A user asks, "What's the weather in Paris?" The model recognizes it can't answer from memory. Weather is real-time data, so instead of guessing, it emits a structured function call, get_weather with city set to Paris. Your application intercepts that, runs the actual API call, gets back 22 degrees Celsius sunny, and injects that result into the conversation. The model then reads that result and formulates the final natural language reply. Notice the model never touched the API directly. It just spoke the language of intent, and your code did the rest. This matters because LLMs have hard limits baked in by their training cutoff. They can't access live weather or stock prices. They're notoriously unreliable at arithmetic, and they have no native ability to make network requests or query a database. Function calling is the bridge. The model handles language and reasoning. External tools handle execution and facts. Train your model to recognize when it needs a tool, and you've dramatically expanded what it can reliably do. The tools list is the vocabulary your model learns to speak. Each entry is a dictionary with 3 fields: a name, a description the model uses to decide when to invoke it, and a parameters block describing what arguments the function accepts. Here you're defining 3 tools: get_weather for live weather data, calculate for mathematical expressions, and search_web for open-ended queries. The descriptions aren't just documentation, they're what the model reads at inference time to decide which tool fits the situation. Write them precisely. The full loop is: user query arrives, model decides a tool is needed, model outputs a structured function call, your code executes it and returns the result, model incorporates that result into its final reply. Every advanced capability in this lesson builds on some variation of this loop. This conversation example shows the complete message sequence your training data needs to capture. The system message establishes that the assistant has access to specific functions: get_weather, calculate, search_web. The user asks about Tokyo's weather. The assistant's reply isn't a guess. It's a properly formatted function call with the right arguments. The next message simulates the system returning the result, temperature and conditions. The assistant then reads that result and delivers a clean, natural response to the user. Every one of these turns needs to appear in your training data, including the function call turn and the result injection turn. If you only train on the final reply, the model never learns the intermediate reasoning. This example introduces sequential function calls, and it's worth paying close attention to the structure. The user asks the model to compare weather in London and Paris. The model can't do that in one shot, so it calls get_weather for London first, receives the result, then calls get_weather for Paris, receives that result, and only then synthesizes a comparison. Notice the model doesn't skip ahead or hallucinate the second city's data. It waits for each result before proceeding. That patience, that willingness to chain tool calls rather than guess, is exactly what you're training into the model with examples like this. What this pattern teaches is multi-step reasoning under uncertainty. The model learns that some answers require gathering multiple pieces of evidence before drawing a conclusion, and that sequential function calls are the right mechanism for doing that. This Python implementation wires the whole loop together. Mock functions handle get_weather, calculate, and search_web. They return plausible data without hitting real APIs, which keeps development fast. Those functions are registered in a dictionary keyed by name, so dispatch is just a lookup. The execute_function_call function uses a regular expression to parse the model's output for the function call pattern, extract the function name and arguments, and invoke the right handler. Pay attention to the error handling here. If the model outputs a malformed call, you want a clean failure message injected back into the conversation, not a Python exception that crashes the session. The chat_with_ functions loop ties it all together. Generate a response. Check whether it contains a function call. Execute if so. Inject the result. Generate again. That cycle continues until the model produces a plain reply with no function call embedded. Technique 2. Structured output generation. Structured output means the model emits machine parsable data, typically JSON, with no surrounding prose, no apologies, no markdown fences unless you explicitly want them. The example here is minimal on purpose. A JSON object with a name field set to John and an age field set to 30. That's the target behavior. When a downstream system calls your model expecting JSON, it needs exactly that. Nothing more, nothing less. The challenge isn't getting the model to produce JSON once. It's getting it to produce valid JSON every single time. This training example shows exactly how to wire the system prompt for structured output. The system message says respond only in valid JSON format. No hedging, no here is the JSON, just the object itself. The user provides a natural language input. John Smith is 28 years old. The assistant's response is a clean JSON object extracting name and age, no preamble, no explanation. The model learns from this that structured output mode means the JSON is the entire response. The system prompt instruction and the training example format must be consistent. If your training data ever includes extra text around the JSON, the model will learn that extra text is acceptable, and you'll fight that at inference time. The key constraint is twofold. The system prompt explicitly demands JSON-only output, and every single training example must honor that constraint. One example with surrounding prose is enough to teach the model that prose is sometimes acceptable. Training data quality here is not negotiable. The generate_JSON_only function adds a retry loop on top of the model call, up to 3 attempts. This matters in production. Even a well-trained model occasionally produces malformed JSON, especially at higher temperatures or with unusual inputs. The function constructs a system message demanding valid JSON, generates a response, strips it down to just the JSON portion, and calls json.loads to validate it. If a schema is provided, it checks that required fields are present before returning. On failure, it retries with an even more emphatic prompt. The output you're looking for is a successfully parsed Python dictionary, Something like name Sarah, age 25, company Google, confirming the model produced valid, schema-compliant JSON on the first or second attempt. Technique 3. RAG, Retrieval Augmented Generation. Here's the fundamental problem RAG solves. Your model's knowledge is frozen at its training cutoff. It knows nothing about your internal documentation, your product database, or anything that happened last week. RAG fixes this by retrieving relevant text at query time and injecting it directly into the prompt. The model doesn't need to memorize your data. It just needs to learn how to read and reason over context that's handed to it. The pipeline has 4 stages. First, the user submits a question. Second, a retrieval system, typically a vector database, finds the most semantically relevant documents from your knowledge base. Third, those documents get injected into the prompt alongside the question. Fourth, the model generates an answer grounded in that retrieved context. The model's job isn't to recall facts from training, it's to read the provided documents and synthesize an accurate answer. That's a fundamentally different skill, and it's one you can teach through fine-tuning. This training example establishes the behavioral contract for RAG. The system message tells the model, answer only from the provided context, don't invent information. The user message includes a context block, in this case a passage about Python's history, followed by a question. The assistant's response pulls the answer directly from that context. Guido van Rossum created Python. Notice the model doesn't add background knowledge or embellish. It reads the context, extracts the answer, and stops. That discipline, staying within the context boundary, is what you're training for. A model that ignores the context and falls back on training knowledge defeats the entire purpose of RAG. This example adds 2 important behaviors on top of the basic pattern: multi-document context and source citation. The user provides 2 documents, one about Paris being the capital of France, one about its population, and asks about the population. The assistant answers correctly and cites the specific document it drew from. Training with citation examples like this produces a model that's auditable. When your system returns an answer, users and developers can verify exactly which source supported it. That traceability is critical in any domain where accuracy matters: legal, medical, enterprise knowledge management. The 3 behaviors you're training simultaneously. Use only the provided context, cite your sources, and explicitly acknowledge when the context doesn't contain the answer. That last one is especially important. A model that admits, I don't have that information in the provided context, is far more trustworthy than one that fabricates a plausible sounding answer. This simple RAG implementation shows the full retrieval pipeline in Python. The class loads a sentence transformer model. All menelm L6v2 is a solid default and uses it to encode documents into embedding vectors when you call add_documents. At query time, retrieve encodes the query, computes cosine similarities against every stored document embedding, and returns the top k most relevant passages. The chat _with_rag function assembles those retrieved passages into a context block, prepends it to the user's question, and passes the combined prompt to your chat model. Watch the output carefully. It prints both the retrieved context and the model's response. If the retrieved context looks irrelevant, your embedding model or your document chunking strategy needs attention. If the context is right but the answer is wrong, the issue is in model fine-tuning. Technique 4. Agent-style behavior. Well, Monda is and practice. You'll master these techniques quickly. An agent isn't a special architecture. It's a behavioral pattern. The model plans by decomposing a complex goal into discrete steps. It acts by executing each step, typically through tool calls. It observes by reading the result of each action. and it adapts by revising its plan when results are unexpected. That four-stage loop, plan, act, observe, adapt, is what separates an agent from a simple question answering system. You train it by providing examples where the model explicitly narrates its reasoning at each stage. This conversation example walks through the full agent loop on a concrete task. Find the warmest city among Tokyo, London, and Paris. The model doesn't just guess. It lays out an explicit plan. Retrieve weather for each city, compare temperatures, report the warmest. Then it executes that plan step by step, calling get_weather 3 times and updating its working state after each result. Finally, it synthesizes Paris at 22 degrees Celsius is the warmest. Notice the model narrates what it's doing at each step. That narration isn't just for the user. It's the model's reasoning trace, and it's what makes the behavior debuggable and trustworthy. Train on examples with this level of explicit step tracking. The 3 things this pattern teaches: make the plan explicit before acting, execute steps in order without skipping ahead, and synthesize a final answer only after all evidence is gathered. That last point is the hardest to train. Models naturally want to answer immediately. Explicit planning examples override that tendency. Complete advanced chat training script. The create_advanced_dataset function generates a synthetic training corpus covering all 3 capability areas in one pass. The first loop produces 50 function calling examples, each one a complete conversation, including the tool invocation and result injection. The second loop generates RAG examples where the assistant answers strictly from provided context. The third loop creates agent behavior examples with explicit multi-step planning. Everything gets serialized to a JSON-AL file, one JSON object per line. When the script completes, it prints the total example count. That number is your sanity check. If it's significantly lower than expected, something in the generation logic fails silently. This dataset is what you'll feed directly into your fine-tuning pipeline. Advanced Capabilities Checklist. Before moving on, run through this checklist against your implementation. For function calling, does the model correctly decide when to invoke a tool, use the right syntax and parameter names, and handle multi-step sequences without skipping steps? For structured output, does the model emit valid JSON with no surrounding text every time across varied inputs? For RAG, does the model stay within the provided context, cite sources, and explicitly decline to answer when the context is insufficient? For agent behavior, does the model produce an explicit plan before acting, execute steps in declared order, and synthesize a final answer only after all observations are in? Any gap in this checklist points directly to a gap in your training data. Key takeaways. Here's what to carry forward. Function calling means the model generates tool invocations. Your application code executes them. Structured output requires training exclusively on structured examples. A single inconsistent example degrades the behavior. RAG teaches the model to respect context boundaries and cite sources rather than hallucinate. Agent behavior emerges from explicit planning examples, not from architecture changes. All 4 techniques compose. You can train a single model that does all of them. And across every technique, training data quality is the dominant factor. The model learns exactly what you show it. What's next? You've now built a model that can call tools, produce structured data, reason over retrieved context, and plan multi-step tasks. The next challenge is getting that model into production efficiently. Lesson 5.6 covers optimization and deployment, quantization, serving, latency tuning, and everything you need to go from a fine-tuned checkpoint to a system that handles real traffic. Additional resources. For deeper reading, the OpenAI Function Calling Guide covers the schema design patterns in detail. The RAG survey paper by Lewis et al. Is the canonical reference for retrieval augmented generation. The React paper, Reasoning and Acting in Language Models, is where the plan, act, observe loop was formally described, and it's worth reading in full. LangChain's agent documentation shows production implementations of everything covered here. Your model now has the behavioral foundations of a capable agent. The final lesson puts it in front of real users. Few-shot prompting is one of the most reliable tools in your prompt engineering kit. The structure here is clean. The system message declares the model's role as a sentiment classifier, and then 3 examples demonstrate the input-output contract before the actual query appears. I love this product maps to positive. Terrible experience maps to negative. It's okay, I guess, maps to neutral. When absolutely brilliant arrives as the live input, the model doesn't need to reason from scratch. The pattern is already established. The key insight is that the examples aren't just helpful hints, they're behavioral constraints. The model learns from the few-shot context that the only acceptable outputs are positive, negative, and neutral. No elaboration, no hedging, no explanation. Format your examples to reflect exactly the output behavior you want. This train problem is a clean illustration of chain of thought reasoning and why it matters for fine-tuning. Train A departs at 9 a.m. at 60 miles per hour. Train B departs at 10 a.m. at 80 miles per hour. The naive approach is to guess or apply a formula blindly. The chain of thought approach makes each inference step explicit. Step 1. Train A has a 1-hour head start, covering 60 miles before B even moves. Step 2. B gains on A at 80 minus 60 equals 20 miles per hour. Step 3. At 20 miles per hour relative speed, closing a 60-mile gap takes exactly 3 hours. B departs at 10 a.m., so they meet at 1 p.m. Notice that the answer falls out naturally once the intermediate steps are stated clearly. When you train with examples structured this way, problem, explicit reasoning chain, answer, your model learns to produce the reasoning, not just the result. That's what makes it reliable on novel problems rather than just pattern matching to memorized answers. This diagram shows the tool calling execution loop from the model's perspective. A user request arrives at the LLM. The model checks whether any registered tools are relevant to the task. If yes, it emits a structured tool called JSON, not a natural language description of what it wants, but a machine-readable specification of which function to invoke and with what parameters. Your application parses that JSON, routes to the correct tool or API, executes it, and returns the result. That result flows back into the LLM, which incorporates it and generates the final response. The critical thing to understand is that the LLM never directly touches external systems. It communicates intent through structured output. Your runtime handles execution. This separation is what makes tool calling systems composable, testable, and safe. 4 prompting patterns worth knowing and when to reach for each one. Chain of thought is your default for anything involving math, logic, or multi-step reasoning. Train with rationale plus answer pairs, and the model learns to show its work. Tool calling is for tasks that require external facts, leave data, or computation. Train with complete tool call sequences, including the result injection turn. The React pattern interleaves thought, action, and observation in an explicit cycle, making it ideal for agentic tasks where the model needs to adapt based on intermediate results. Use React trajectory data for this. Self-consistency is different from the others. It's an inference time technique where you sample multiple completions and take a majority vote. No special training required. Just run the model several times and aggregate. Reach for it when you need high confidence on a single high-stakes answer and can afford the extra compute. System prompt engineering is where a lot of fine-tuning gains get lost or amplified. 7 practices that consistently matter. Be explicit about the model's role. State what it is and what it's for, not just what it should do. Define the output format precisely. JSON, Markdown, plain text, specific schema, because ambiguity in the system prompt produces inconsistency in outputs. Enumerate constraints as explicit negatives. Do not statements are often more effective than positive instructions alone. Add inline examples for any non-obvious output pattern. Few short examples in the system prompt are powerful even after fine-tuning. Specify tone and register, formality level, person, and voice all affect how the model communicates. Keep every prompt testable. If you can't write an eval for it, you can't measure whether it's working. And version your system prompts alongside your model checkpoints. When behavior changes, you need to know whether it was the model or the prompt that changed. The function calling schema has a specific anatomy your model needs to learn. The tools array contains one object per available function. Each object declares its type as function and then provides a nested function definition with 3 fields: name, description, and parameters. The name is what gets emitted in the function call output. It must match exactly what your dispatcher expects. The description is what the model reads to decide whether this tool is appropriate for a given query. Write it from the model's perspective, not the developer's. The parameters block uses JSON schema format, an object type with a properties map where each property declares its type and description, and a required array lists which parameters must be present. Get the schema structure right in your training data and the model learns to emit well-formed calls. Get it wrong and you'll spend hours debugging malformed JSON at inference time. Different tasks call for different output structures, and your model needs training examples for each one you intend to use. JSON output is the right choice when a downstream system needs to parse the response programmatically. Strict formatting, no surrounding text. Markdown sections work well for complex responses that humans will read. Headers create navigable structure. Step-by-step numbered output is ideal for instructional content where order and completeness matter. Table output using pipe delimited formatting handles comparative or structured data cleanly. Code block output with fenced syntax highlighting is essential whenever the response includes executable code. The fences signal to renderers and parsers that the content is code, not prose. The pattern across all of these is the same. Pick the format that serves your use case. Build training examples that demonstrate it consistently, and make sure your system prompt specifies it explicitly. Mixing formats in training data without clear system prompt differentiation is a reliable way to produce inconsistent outputs.